With this section, we're going to introduce the concept of isolation in our DC to DC power supply. And so we're going to start with describing some of the theory behind the isolation process, and then talk a little bit about some products that should be interesting to you. So the first module here is describing the issue of isolation. Isolation typically means that we put a transformer in the power path somewhere to be able to isolate the high voltage from the users who might be have their hands on the power supply around its output. So safety is first and foremost a requirement or a driving force for isolation. But typically, that's not typically, actually voltages less than 60 volts, safety is not normally required because that has been defined as a non-hazardous voltage. So for the DC to DC controller we're talking about today, safety is not the reason for the isolation as much as the possibility of giving us efficient change in voltage level, and some of the other benefits that come with isolation are perhaps being able to have separate grounds to prevent noisy grounds from getting into sensitive circuitry, or to possibly do some level shifting to generate voltages that are at some other, or reference to some other voltage besides ground, or the possibility of just generating multiple voltages, positive and negative, for example. All are aided substantially with the application of a transformer in the power path. Now, in its simplest operation, we've shown a schematic of two power stages that have incorporated a transformer for isolation. And by isolation, what I'm meaning is there's no DC current path from the input to the output, assuming that we had high voltage on the input and there's a safety consideration on the output. But regardless, introducing the transformer separates that, so while we can pass AC signals through a transformer, we can't, there's no DC current possibility going through there. So the one on the left is a isolated version of our standard buck circuit that we've been talking about in earlier sections. You see the output circuit, which has a simple LC output filter, a freewheel diode for conducting when there's no power coming from the primary source. And then we've added a transformer between this output circuit and the input, which we're switching by switching current through the primary of the transformer. This transformer is configured so that the dots indicate polarity. When the switch is closed, current flows through the primary from the input voltage down through the primary, and the positive end of the positive voltage of the primary winding at the dot is the positive voltage of the secondary, and during that time it's at a positive voltage which forward biases that output rectifier and passes current through the inductor and onto the output. And then when the switch is opened and current is stopped in the primary, it also is stopped in the secondary. That means that the rectifier in series with the secondary serves as a blocking function, and now the only place where inductor current can flow is through the freewheeling diode up from ground and directly to the output filter. So this is the buck circuit with only a transformer that is inserted between the power switching and the output filter. The circuit on the right looks the same almost, only we have arranged the transformer so the polarity is different as shown by the dots. Now, when the switch is closed and the primary gets positive voltage at the dot, the positive voltage is at the lower end of the secondary, which means the upper end is negative, which means that diode cannot conduct, and the only current that can flow at all is from the output capacitor on out to the load. There's no secondary current flowing. So the question is, well, how does it get there then? And the answer is, well, when the switch is opened and current that was flowing in the primary side of this transformer, the primary winding. That current has to, because of that inductance of that primary winding, that current has to continue to find a path to flow. It's coupled over to the secondary, and now it can flow with the polarity in the right form to forward bias the diode and deliver current to the output. So this is like the flyback circuit in a non-isolated state. It's a two-step operation. One step, we drive the primary and store some energy in the transformer, and in the other step is when we disconnect the primary, and that energy then is transferred to the secondary and on out to the output. And the implication of that is the output capacitor has to work a lot harder because it has to deliver load current all the time and out of its own charge when there's no secondary current flowing, and then hopefully getting recharged when the secondary current flows. So while the schematic for these two transformers looks the same, they are significantly different in their performance. The flyback circuit has energy storage capability. It's characterized by the inductance of the primary circuit, and its purpose is to store energy in that inductance. The circuit on the left, which is in the forward, is supposed to just transfer energy. We want as little energy as possible, so that transformer is designed as tightly coupled as possible, and with the expectation is current flows in both windings at the same time, and it stops flowing in both windings at the same time. So what we have on the left is what I would call a true transformer. What we have on the right is what I would really call is a coupled inductor. It's an inductor with two windings, an input and an output. And the one on the left, we don't want any internal storage. There will be a little because there is some leakage inductance inherent in any transformer, but very small. And in the right, we have inductance as a major parameter because that's what allows us to store energy. Now that introduces the concept of magnetic devices, and we could spend a lot of time talking about that, and we don't have the time to do it. Let me just say that this graph, this curve that you see, this hysteresis-shaped curve, is a description of the magnetic characteristics of a magnetic device. And what they're plotting is magnetic field in the horizontal direction versus magnetic flux in the vertical direction. And two gentlemen of ages past defined this by Mr. Ampere. He determined that a magnetic field could be generated with a certain number of turns of wire in a coil and current passing through the through that coil. So there's a current relationship between magnetic field, and between the magnetic, or that helps define the magnetic field. Faraday, on the other hand, was looking at the flux levels and found that the magnetic flux could be increased by a voltage across a coil of wire that lasted for some period of time. So it is the integral of volt-seconds that determines the flux density in the vertical axis. And the relationship between these two is defined by the magnetic material itself, and that forms the shape of this curve. And the slope of this curve is actually defined by the parameter called the permeability, which is a magnetic parameter that describes the magnetic capabilities of a particular material. Materials that are very poorly magnetic, like air and wood and paper and plastic, have an extremely low permeability, and that curve would be very flat, almost horizontal. And materials that have an excellent magnetic characteristic, a high degree of magnetism capability, would have a high permeability, and that curve would be very vertical, meaning that a very small amount of current would give you a very large flux density. The net result of that is that permeability and the slope of that curve is related then to the storage capability. We want lots of storage capability in a flyback transformer, so that curve will have a shape somewhat like, as shown here, or maybe even flatter, while the curve for a transformer that is intended just to transfer energy, that curve would be much more vertical. That curve has a thickness to it because it takes energy to be able to move up the curve, and as you increase the current, the flux density moves up on the right-hand edge of that curve, and as you terminate the current and the magnetic flux returns back to its low position, it comes back down the left-hand side of that curve. And the area of the curve itself represents the energy that is lost in the magnetic switching process. So every excursion up and back generates some internal loss that has to be accounted for in the design. One other characteristic to keep in mind is that curve tends to flatten at the top on both the top and the bottom of the curve, and that is because any magnetic material has some limitations of how much flux density it can hold before it essentially saturates and will absorb no more. At that point in time, you've lost the magnetic characteristics of the device. The current, if not externally constrained, can go out to destructive levels. And so whenever you look at these curves, you have to be able to recognize you want to operate well below where that curve tends to flatten out. You want to stay away from saturation. One other thing to point out of the curve is that it is not polarity sensitive. You can see that the first quadrant and the third quadrant have exactly the same characteristic. A magnetic device doesn't care which end is the North Pole and which end is the South Pole. It has the same characteristics in both directions. Most of our power supply circuits tend to want to use the excursions in the right-hand quadrant, the upper right, the first quadrant, because we're talking about positive currents and positive voltages, but not all. And so there is the possibility of extending the usage of the curve. Looking at those two circuits that we talked about earlier, the forward and the flyback, here are the current waveforms shown in the transformers and the output capacitor, just to illustrate the different performance characteristics of those two circuit topologies. On the left, we're talking about a forward, which is like a buck circuit with just a transformer, and we're plotting in the first waveform the primary current, which you see going up when the switch is closed and then ramping up as it senses the output inductor in the circuit. And then when the switch opens, the current goes back down to zero. And the secondary follows that current very closely with, of course, a turns ratio relationship. If the turns ratio isn't 1-to-1, the current would follow the turns ratio. And what we're seeing in the capacitor waveform is the output capacitor now, which gets recharged when the primary and secondary currents are flowing, and which gets discharged when the current is only in the output inductor, which is not shown there, but that occurs when the transformers is not conducting any current in either winding. So the current in the capacitor is just a small AC ripple current caused by the value of the output inductor, which we talked about in earlier modules. The flyback, remembering again, it's a two-step process. If you look at the primary current, when you close the primary switch, you generate current that ramps up. During that time, that energy merely goes into increasing the energy stored in the transformer's inductance. In the secondary, you can see that during that time, there's zero current flowing because the secondary rectifier is blocking current in the polarity that it would have to be to conduct. And then when the primary switch turns off, the current transfers to the secondary, so it picks up exactly where it left off on the primary, but now that inductor stored energy is being delivered to the output capacitor and recharging the output capacitor. And you see that in the capacitor current waveforms down on the bottom right, where the capacitor current when the secondary current is flowing, it gets all that current into the capacitor, and it's going into the capacitor, which is above the zero reference point. And then when the primary side is conducting and there's no current in the secondary, the current in the capacitor is a negative constant current because the output voltage is constant coming out of the capacitor. So you have high AC currents in the capacitor. You have higher peak currents in the transformer windings because you've had to put all the energy in during just portion of the cycle that the switch is closed, where over on the forward, you had energy flowing continuously through, so the peak current levels are lower. So, distinct difference between the two. So here is what our generic isolated power supply would consist of. Now we've been talking just about the blocks on the upper portion of that block diagram, where we have a power stage driving the primary of a transformer that is coupled to a secondary, which drives the output, rectifier, filter. Well, in this case, just the output rectifier, remembering that if it's a forward topology, there is an output inductor in that rectifier block. If it's a flyback, the inductor's in the transformer, so there's nothing but the rectifier itself in that block, and then the output capacitor is shown outside it. But that's not the complete power supply. You can see that the transformer does provide the safety isolation and all the rest that we want for isolation, but we haven't controlled the switching yet. We have to sense the output voltage, which is over on the secondary, and generate, compare it with a reference, generate an error signal, and generate some kind of a command that it has to get back over to control the pulse widths of the power switches on the primary side. So that takes another crossing of the isolation boundary. Now typically that's just a signal level, and it's usually done with just an optocoupler, but there is some involvement there with that optocoupler that can get to be a problem and is worth finding some improvements over that. But essentially, the feedback signal also has to be isolated, and this block diagram shows it, and it shows it in this case of an optocoupler providing that isolation. So that's as far as I wanted to talk about the power stage. Now I want to show you a couple of the next module in this program will cover a couple of product designs that take advantage of the transformer and give us some isolated DC output voltages.